Hey guys, last time on 5.3 we talked about the exponential rule and also about the log rule. So I think we can pretty much summarize all the integration rules so far that we learned by this table in here. I split them into two tables. These are for like the basic ones and these are for the new ones. Okay, so then pretty much the derivative of e to the u would be itself. But then if you have like a chain rule, if you have like some other function, write an x on the exponent, then you will have to take the derivative of that exponent and times it by the e function in here. Okay, and similarly the derivative of 1 over u, or u to the negative 1, it is ln u in absolute value, because for ln we cannot take like 0 or any negative numbers, right? But of course, if you have like other function rather than x on the bottom of the fraction, then you have to take the derivative of that denominator and then times it with the ln u in this case, okay? And make sure whenever you do the integrals in there, make sure you always attach the plus c in here. Okay, so let me do that again, and then this one. These I didn't do it out, so that's why we don't have a plus c, but then we do have a plus c in here and in here, okay? So make sure you write them as a family rather than a single function, okay? And as for today, let's talk about area and definite integrals. Okay, from geometry, we know that the area is a number that defines the size of a bounded region. For simple regions, such as rectangles, triangles, and circles, area can be found using geometric formulas, right? Like we know that the formula of the area of a rectangle is base times height, or you can say like length times width, and then the area of the triangle is 1/2 base times height, or 1/2 the length of the two legs times together. And then the area of the circle, if you still remember the formula of it from like geometry, that goes like a equals to pi r squared, where r in here is the radius of that circle, right? So those can be found by geometric formulas, right? But then what if we have some other ugly like forms or like shapes, right? So in this section, we will learn how to use calculus to find the areas of non-standard regions. And what do I mean by non-standard? I mean, we're not talking about like rectangles, circles, or triangles in here. We talked about some like bowl shape like this. Okay, let me put it back. Okay, so just imagine if you're gonna have like a bowl, like, okay, I'm not a best drawer, but you can imagine this is a bowl, right? So then we can imagine the area of the bowl in here. We can calculate it using calculus, or in other words, using like integration, okay? Or sometimes we're gonna have some shape that is close to a triangle, but it's not a triangle, right? Like this one in here has some curves to it, so it's not gonna be like a complete triangle, like the standard triangle, but it's like a bending triangle, okay? So with integration, we'll know how to calculate different shapes, the area of different shapes in here, okay? All right, so let f be a non-negative and continuous function on the closed interval AB. So in here, let me put function in here really quick because that's what I miss, and I'm going to update it on the worksheet too. The area of a region bounded by the graph of f, the x-axis and the lines x equal to a and x equal to b, is denoted by the area of the integration going from a to b of f of x dx. Okay, so then the information that you can find here is, because it's like trapped, it's bounded between x equal to a and x equal to b. That's why we have a in here as a low limit and b in here for the upper limit, right? And because we talked about a function f, that's why the integrand in here, the inside of the function, it will be f. Okay, and I think I can do a better job at this one, so bear with me. So this one, that one is in pink, and then this one, let me try to put it in green. Okay, there we go. And then the last thing, make sure you guys have to attach it, is dx, right? So I told you guys dx is like a compromise for the integral signal, or like the integral symbol, right? Whenever we have the integral symbol, we always have to have dx or du or dy depending on the variable that we're using, right? So then this expression is called the definite integral from a to b, where a is the low limit of integration and b is the upper limit of integration. Okay, so the key word here to remember is this word definite integral. Okay, so in the past we talked about the indefinite integral already. First of all, let me just cut this one out. Okay, so there's two type integrals, right? So let me put it in pink again, I guess. So there's indefinite integral that we learned in the past, and there is definite integral that we learned for today, right? Indefinite integral, it goes like integral of, you know, f of x dx without bounds, right? So there's like no a and b whatsoever on the integral notation, right? And then as a result, you're gonna get something like f of x, like big F of x plus c, right? But for the definite integral though, you will have something attached to the integral symbol, right? So then it's pretty much just the same thing, but it's just like has a and b in difference, okay? And for this one in here, we're gonna have a number, okay? We're not gonna have a function, but we're gonna have a number. And I'm gonna show you guys how to get a number in a second, okay? But keep in mind about the difference between like indefinite integral and definite integral, okay? Make sure you know the difference. One of them, the indefinite, it has c and it has a function to go with it, where the definite integral, it must end up with a number rather than a function, okay? So then, just like what we have reviewed so far on the first page, here's our rules for the integration, right? So we're gonna see them again for definite integrals. So let me just put it back in red. So we have like these rules again, but if you notice, each of the integral in here will have from a to b, right? So technically this one in here is like whenever you have a constant multiply with an integral, just go ahead and pull that constant out of the integral and go ahead and focus on integrating just the inside or the function, right? And then if we have like a sum or difference in here, you can go ahead and split it into two integrals and make sure you copy the limit of integration in here so it goes from a to b, right? So when you split it out, make sure both of the integrations will have the limit going from a to b. Not one of them, not none of them, but both of them have to have it. Okay, and then for number 3 in here, okay, this one, let me show you a picture of this one. Maybe it will make more sense. So let me go ahead and we'll cut this thing out. All right, so for number 3 in here, it's like a split up integrals, okay? And let me show you the meaning, like the real meaning of why we have to learn integrals. Okay, so just imagine if we're gonna have some, okay, this is like x and y axis, right? So this is y axis and this is an x axis. And I'm gonna give you a function, I don't know, like this function, I'm gonna call it f, okay? And then I'm gonna give you like some limits to integrate, right? So it goes from, I don't know, like a in here and b in here. So as you can see, a in here, it doesn't have to be like the starting point, and b in here, it doesn't have to be the ending point, right? Like a and b could be whatever the problem wants to give us, okay? So it's not our choice, it's the problem's choice, okay? So then what I'm gonna do is that I'm gonna like project a and b toward the function f in here, okay? And then if it asks you to do the integral from a to b of f of x dx, that means I'm asking you to find the area underneath the curve here, the shaded region. Okay, so this in here, the area of it is what it means, like what stands for the integral from a to b of f of x dx. Okay, so in other words, integration, it stands for the area. Okay, so with that saying, just imagine I'm gonna split this into like two intervals. So say, I don't know, let me just put like a C in here in between A and B. And I'm gonna split it out to two different like sections, right? So this is like section 1 and this is like section 2, right? All right, so I'm gonna apply the same rule in here to find the integral. So the green areas in here, it represent, well, for the first one, it goes from A to C, right? And it's we still talk about like f of x, right? Like there's no other function. And then the second function, or the second area in here, it goes from C to B, and we still have the same function, fx dx. At the end, if you can see like the sum of the green areas in here will make the pink area, right? So what we're gonna do is that we're gonna add them together, right? So this in here equals to this in here. Okay, these two are equal to each other. Okay, so as you can see in here, like if you think about a symbol in here, there's like a sneak in the symbols, right? Instead of going from A to B, right, we're gonna squeeze in the C in between. So we're gonna let it go from A to C and then C to B. So A to C, the first one, and then C to B, the second one. Okay, so that's what it means in here. This is what it means by the picture and by the formula. Okay, and make sure your C has to be a number in between, right? Else there's no way to squeeze in like C in between A and B if C is not in between, right? It's like there's no way to squeeze in a 5 in between 1 and 2, right? So if I'm asking you like what to squeeze in between 1 and 2, you have to give me something reasonable. Something like, I don't know, 0.5, 0.1, or 0.2. Again, this is like really depend on the problem sometimes. But yeah, I think it should be reasonable, okay? So make sure like all the numbers like work in there, and make sure them squeeze in like a non-reasonable number in between the two given numbers from the problem, okay? And let's talk about number 4 in here, another scenario. Okay, so just imagine we're gonna have the same picture again. So let me put it in blue. But before that, let me go ahead and take this thing away. Okay, so just imagine we're gonna have the same graph, right? Like X and Y axis in here. And I'm gonna go ahead and give you some curves. It starts from this point and ends from this point. I'm gonna call it F for the curve. Okay, just imagine if I'm asking you the area underneath of the curve from A to A, right? So say A is like right here, right? But we're going from A to itself, from A to A. That means we cannot like generate any area in between, right? Because A is here and then A is like back to itself, right? So then we pretty much just have like a line, right? It's not going to be a section like this. It's not going to be an area, right? It's just like a thin line, right? So that means that we're going to have a 0 in there. Okay, and if you want to think about it, we don't go anywhere, right? Like we cannot expand to the right or to the left of A because it's just stopping at A. Okay, so it has to be 0. Okay, so for example, if I'm asking you to find the area from, I don't know, from 1 to 1 of any function that you want to, well, you don't even have to integrate this one, okay? Like we all know that the integral of x, it will be like x squared divided by 2, but you don't even have to do this one, okay? Whenever you see the limit of integration being exactly the same, you can jump to the conclusion that the area in here equal to 0, regardless what function we have in here, okay? And now let's talk about number 5. Okay, so this one is like a little tweak up in the limit of integrations also. So for the beginning problem, we have it going from A to B, right? But then later on, say if I don't want it to be that way, I'm gonna go backward. I'm gonna go from B to A. But as like to compromise for it, I need a minus in front. Okay, so it's like if you have like x minus 1 and I want to be like special, I don't want to be like you, then I can go ahead and pull out a negative in front of it, and I'm just going to be like 1 minus x in here. Okay, so these two are the same thing, but just instead of, you know, x minus 1, now I'm going to get negative 1 and then 1 minus x. Okay, and if you want to think about it, let me give you guys like a diagram or a picture about it too. So this one again, we have like xy axis, and then we're going to have some curve. Ending point, beginning point, right? And then we're gonna have it going from A to B. Usually I use like dashed line for like the line, the vertical line at A and B, but you know, even lazy like me, then you can do like the straight line, because I'm not gonna ask you guys to like draw the picture of the area. This is just for us to understand the meaning of integration, okay? But I don't think I'm gonna ask you ever to draw them out. All right, so the area underneath of this one, underneath of the curve f in here from A to B, it goes like the integral from A to B of f of x dx, right? But say if I don't want to go from left to right, right? Like if I want to go from right to left, then what I'm going to do is that I switch the upper and the lower limit, first of all, but then this doesn't look like normal, right? Like I cannot just do that like that, right? Because I'm going against the order in here. So to compromise with that, I have to put a minus sign here. Okay, so make sure whenever you switch the limit of integration, you have to like pull out a negative in front of it. Okay, so now let's talk about a quick example before we move on to the real example, right? So what do we have here? Okay, this picture right here, imagine I'm gonna give you a curve, and the function for that curve, or like that graph, is the absolute value of 2x minus 1, right? So then we're gonna have like two pieces for this function. This piece in here, okay, let me try to use another color for this. So this one, let me highlight it in blue, and then say I'm gonna use red for the curve, or for the line on the left hand side, and maybe pink for the line on the right hand side, right? Okay, to refresh our memory about the absolute value in here, so absolute value of 2x minus 1, it can be broken down into two cases, right? The first case is when 2x is, you know, like bigger than 1, right? Like inside the absolute value, if we have some positive number, then when we break out the absolute value, it stays the same, right? But in the second scenario, when we break out the absolute value, and on the inside, if we have some negative value, right, then we're going to end up having a negative in front of it, just like this. Okay? And how do we know when which function will take place, right? So what we're going to do is that we're going to set this function equal to 0, just the inside function equal to 0, and then we solve for x, right? And if you do it correctly, you should get x equal to 1/2, right? So this is like the breaking point. So if you notice right here, this point here is 1/2. And that's the breaking point. On the left of it is always going to be negative, and on the right of it is always going to be positive, or a regular absolute function, okay? So let me go ahead and highlight the right function and also the left function in here, okay? And just to like make it more detailed, the left function is usually the negative one, and then the right function is usually the positive version of what inside the absolute value. Okay? Alright, so by geometry, if the problem asking us to find the area, like the shaded area in here, well, what can we do, right? First of all, if you know this, there's two areas that we need to find, right? There's two triangles that we can find here, which is this one in green, the little triangle in green, and the bigger triangle in brown, right? So the shaded region in there, to find it, we have to find the area of the two triangles in the picture, and then we add them, and then that's the answer, right? So by geometry, we know that the area of a triangle, in general, it equals to 1/2 base times height, right? So now let's apply it, okay? So let's talk about the green triangle first. So it goes like 1/2, and then the base in here. Okay, let me go ahead and clean the picture first, because I feel like there's too much info in here. Okay, so again, this is the green one. That's the bad one. Okay, that's my best. And then this is the brown one. Okay, so as for the green one, okay, give me 1 second. Let me just try to make it look better. Okay, that's the best I can get. Okay, so for the green one in here, the base is this distance from here to here, which is 1/2, because we're not there at 1 yet. And then the height would be this distance from 0 to 1, which is 1. Okay, and then we're gonna go ahead and add it with the brown triangle. And for the brown triangle, the base in here is going from 1/2 to 2. So if you do the math, 2 minus 1/2, if you go ahead and put it in the calculator, you're gonna get something like 3/2, right? So we have like 1/2 from the formula, the triangle area, and then we have 3/2 for the base, and then for the height, it's going from 0 to 3, so we're gonna get 3 in there, okay? So if you do all this and put it into the calculator, you're gonna get 5/2 for the final answer. Okay, so let me put it in green, blue. So 5 Okay, I can do better than that. Let me go ahead and write this one smaller a little bit. So there should be like a 3 in here. And as for the final answer, we're gonna have 5 halves. Okay, so this is the geometry way, right? We haven't talked about integrals so far, right? But in terms of calculus, right, we have another way, we have another method to calculate the area, like all together. So what we're gonna do is that we have a split in here, right? So again, we're gonna still have the green triangle, and we're still gonna have the brown triangle, right? So then for the green triangle, we can write it as the integral going from 0 to 1/2, because 1/2 is where the x stops, right? Like where the triangle stops in the x-axis, okay? And then the function in here, it is negative 2x minus 1, and then dx to compromise for the integral. And moving on to the next integral, for the one in brown, we're going to have it going from 1/2 all the way to 2, because 2 is the stopping point, okay? And then the function in here, it would be 2x minus 1. So notice that we're going to have like a function, a different function for each triangle, right? And that is because of the absolute value, because we have a breaking point at x equal to 1/2. Okay, that's why we have to divide it into like 2 intervals. Okay, and lastly, we're going to have like dx in here. Okay, so let me put the plus in here, and then let me just do each of the triangle out like separately. Okay, and by the way, just see, like, make sure we don't get confused. So this is like one solution, and this solution is by geometry. Okay, and we're gonna have another one by using calculus. So purple maybe in calculus. Let me also change this one to purple so we don't get confused between the colors. So then for the green integrals in here, okay, first of all, you're gonna distribute the negative into 2x and into the -1, right? And after you do like all the crazy math in here, you should get something like negative x squared plus x going from 0 to 1/2. Okay, and I'm running out of space, so let me just move this thing a little bit further. Here, this should be good enough, I think. Yeah, that should be good enough. Okay, so let me complete this one again, and this one is a calculus way. All right, so what we're gonna do is that for the green part in here, we're gonna go ahead and plug in 1/2, the top number, the upper limit, into each of the term while we have x. Okay, and if you were to do it correctly, you're gonna get -1/2 squared, which is a -1/4 plus 1/2, and then after you put it into the calculator, you're gonna get 1/4. Okay, and now talk about the lower limit. You're gonna do the same thing. Wherever we have x, we're gonna plug 0 in. Okay, and then if you do it correctly, you're gonna get 0, right? And then the next question is that, well, we have 2 goals, right? The first goal is for the upper limit, the second goal is for the lower limit. But what we're gonna do with those 2 numbers, right? And the answer is that we're gonna subtract them. Okay, so let me go for orange in here. Subtract them. Okay, so just to confirm in here, this one is from the upper limit, and this one is from the lower limit. Okay, so as for the answer for the green triangle, we're gonna get 1/4. Okay, and if you notice, it's the same thing as we have in here, right? Like 1/2 times 1/2 times 1 is 1/4, right? And talk about the other one, the brown triangle. We're gonna do the same thing pretty much, but in this case, we don't have to distribute any negative, right? Because we don't even have any negative. So you're just gonna go ahead and integrate each of them, and if you do it correctly, you're gonna get x squared minus x, right? And then it's going from 1/2 to 2, right? So then now what we're going to do is that we plug in 2 for each of the x term in here. So then if you do it correctly, you're going to get 2. And then if you do the same thing for 1/2, you should get 1/4, right? And similarly to the same logic that we did from the last time, this one is for the upper limit and this one is for the lower limit. So we're going to go ahead and subtract them. And then the answer for this one is going to be 7/4. Okay? Okay, so what is the final answer, right? So I told you from the beginning is that to get the shaded area, the area of the shaded region in here, we have to add the green and the brown triangle together, right? So that means that we have to add 1/2 together with 1/4 together with the 7/4, right? And if you add them correctly, you're gonna get something like 8/4, which is 2. So hold on, I think I make some mistake in here. I know. So this one, it should be a negative rather. Okay, and then the answer in here should be 9/4, not 7/4. And you know what? Let me write this one again so that I don't confuse you guys, because I don't want to squeeze in the information in here too. Okay, so for the 2, we're gonna get a 4, right? And then move on. Minus for the the break between upper and lower limit. For the other one, if you were to do it correctly, you're gonna get -1/4. And again, this is for the upper limit, the 4 is for the upper limit, and then the -1/4 is for the lower limit. Okay, and then brow. If you do it correctly, if you were to add them together, what do we get in here? Oh, you know what? This one is a 2, my bad. I get all the number mixed up for no reason. Okay, so this one is 8 + 1, which is 9, so it should be 9/4, right? And then to get the final answer, we're gonna go ahead and add these green and brown area up. So then we're gonna get 10/4, right? And then we simplify to get 5/2. And this is the same result that we get from above. Okay, but then this one, the blue one is from geometry, and then the purple one is from calculus. Okay, I know you guys might ask me why do we have to use a calculus way? We have the geometry way already. The geometry was way easier, right? But then unfortunately, this one is a nice case. That's why you can see the way with geometry right away. But then sometimes you cannot do it, right? If it were not to be a triangle shape, then we cannot use it by geometry ways anymore, right? Because we don't even have any formula for a non-standard shape, right? So calculus is the way to go. Integration is the way to go. Okay? So let me talk a little bit about the setup in here. Okay, so notice that at the beginning of the question, I write this expression in here, right? So what does it mean, right? It means that if you know this, okay, let me clean this one up too. Okay, so red. Okay, just imagine here, this one is your curve, right? So it goes from here to here. And why do we go, okay, you know what? Let's just put the whole curve down. So this one is the f function, or the curve that we have, right? And then we have A going from 0, and then B going to stop at 2, right? So that's why earlier, this one for the limit of integration, I have it going from 0 to 2. And for the function, I just copy and paste this function given from the problem, right? And then dx is just the attachment to compromise for the symbol of integral, right? But after that, though, make sure you have to break it down to 2 cases, because we do have a breaking point at 1/2, just like how we discussed earlier, right? And that's explained why sometimes this one is absolute value, but then this one has a negative, and this one, it doesn't even have anything in front of it. Okay, so it's it's based on the function that you have, and it's also based on the graph of the function that you have. Okay, so now let's talk about the very first objective, the fundamental theorem of calculus. Actually, we already did it, but I just didn't give you the name. So now I'm going to introduce it properly with you guys. Okay, so what about a fundamental theorem of calculus? It tells us that if f is a non-negative and continuous function, again, I don't know why I keep missing. Oh, maybe, okay, I don't even need a function because f in here is already stand for function. And I think same goes for the last case. So I guess we don't have to really edit this one. So f in here is already like a shortcut for function because, you know, f is start for function. So then if f is non-negative and continuous on the closed interval from a to b, then the area or the integral from a to b of f of x dx equals to f of b minus f of a. So let's break it down, right? So the a and the b in here, those that come from the limit of integration, right? And then the f's in here, the big f's, they come from the integral of little f, right? So you have to do something to integrate the original function, and then you plug in the upper limit, and then you plug in the lower limit, and after that you subtract the two numbers. Okay, so make sure you don't plug in the numbers, the limits, like right from the beginning. Okay, so I get some like couple cases from the past, and make sure you don't do the same mistake. Okay. All right, so personal tips when it comes to rational functions, we have to perform long division, like what we learned in the last example. Where you have like a function on the left hand side, something, I don't know, like x squared minus 4, and then something simple like x plus 1 on the right side, left hand side, like this. And then just a quick reminder about the long division is that on the left hand side, if you notice in here, we're missing an x term, right? We have the x squared, we have the free number, but we don't have anything about the x term. So that means we have to space out some spot, and then we have to squeeze in the x term, giving 0 as like the front number for it. So let me just put 0x in here to save a spot for the x term, and then return the minus 4 at the end. Okay, so then if you don't remember how to do it here, let's do it with me as a good practice for the long division. Okay, so if you have your own paper in there, let's just practice, and then we can compare the answer in here. It goes like we're gonna have to divide the x squared with the x because they are the leading terms, and x squared divided by x, I'm gonna get an x in here, and I multiply them back, so I'm gonna get x squared plus 1x, right? And then bar in here, and then next up I have to change the sign of everything, right? So this one from positive is gonna become negative, and for the other one it'll be negative also, right? So these two cancel, and then I'm going to get negative 1x in here, and I'm going to bring down to 4 like this. Okay, next up, we're going to go ahead and divide the leading term by the leading term, right? So what do I get after that? Well, I'm going to get a negative 1 for this, right? And I'm going to go ahead and multiply them back to get negative 1x minus 1, right? And then the bar. And then we're going to go ahead and change the sign on the second row, like what we usually do. So let me put it in pink. And this one will be like plus, the other one is also plus, right? So these two, they canceled out, and then this one, it gives me like a negative 3. And as for the final answer, I'm going to rewrite it as, so from the beginning of the problem is x squared divided by 4 divided by x plus 1, right? The answer of it is x minus 1 coming from here, minus or plus the remainder if you want, 3 coming from here. Whoa. So the negative 3 coming from here, and then we're going to keep the same denominator as we had from before. Okay, so this is the final answer for that long division. If you want more practice of it, you can make up like some function to play around with it and send over the work to me for, you know, checking your answer. Okay, so let's take that out, and let's go back to the example that we have on this page. Okay, so we have to find the area of the following bounded region, right? So the function is given already from the problem. And obviously in here, because the power of the top is 2, which is greater than the power of the bottom, which is 1, that means we have to perform long division, right? So another good practice for long division. So first step first, long division, I'm going to do x squared And then, like what I said earlier, we have to save some spot for the 0x because we don't have any x term, right? And then we're going to get a plus 4 in here. And on the right-hand side, we just have x. Okay? So I'm going to do it pretty fast. It goes like x in here, multiply it back to get x squared plus, no plus, right? It's just one term. And then I'm going to go ahead and change the sign of it. So then I'm going to rewrite down 0x plus 4, but I keep telling you guys the 0x in there, it just doesn't mean anything. So you don't even have to bring it down. You can just ignore it. Okay? So then this one in here, when it comes to 4 in here, well, 4 divided by x, we cannot do anything with it, right? Because like the power of 4 is 0 and the power of x is 1, right? So we cannot continue to perform the long division. And hence, we can rewrite this fraction from the beginning in here. It equals to this x plus the remainder 4 divided by the same bottom or the same denominator that we have from the problem. Okay, so now we're going to focus on this one to find the integral. Okay, so this is like step 1 if you want to like label them out. Long division. Step 2, the real work, the real math. Integral. So we have integral of the function f, which is x plus 4 divided by x. I would appreciate it better if you put them in parentheses because they come together as a group, right? So they're not like a single term, but they are together as a group. And then for the limit of integration, if you notice, it starts from 1 and it ends it at 4, right? So we can go ahead and put 1 in here and 4 in here. Okay? And here comes the work. I'm pretty sure you guys are like familiar with how to integrate x and 4 of x already. So let me skip forward to that. It's going to be x squared divided by 2. And then for the other one, we just learned that the integral of 1 divided by x is ln of x, right? Or ln of absolute value of x, right? And the 4 in here is a constant, so we can just pull it out like this. And then ln of absolute value of x. Okay? And then I'm running out of space, so let me just move this thing a little bit to the left. Okay, and then put them in parentheses, and then the limit of integration, it goes from 1 to 4. All right, so what we're gonna do, we're gonna plug 4 into wherever we have x. Okay, so then I'm gonna end up having, what is it? 8 minus 1/4, which is 31 over 4. Okay, and let me use another color code for this one, I guess. Yeah, definitely. Let me just go for another like number or color. So plug in 4 in here, and in here, you're gonna get 31 divided by 4. Okay, and then green, the low limit, 1, right? If you plug 1 into here and into this x, you're gonna get -7 divided by 2, right? And then as for the FTOC, the fundamental theorem of calculus, we have a minus in between, right? We have to minus the low limit from the upper limit, and if you were to do it correctly, you're gonna get 45 divided by 4, and this is the perfect like final answer that we get for this problem. Okay, and just a reminder in here for this problem in here, I mean there's no way that we can find the area of this shape by geometry, right? Because it doesn't look like a regular shape. It's not like a cylinder, it's not a triangle, it's not a square, it's not a rectangle, right? So again, integration calculus is the way to go for. Okay, and as for your problem, you're gonna do this problem right here. Okay, and if you want me to help you guys set it up, we have like the integration in here. I'm gonna go ahead and copy and paste the function down. So we're gonna get 3e to the negative x divided by 2 dx. Okay, and then the limit of integration is going from 0 all the way to 4, right? So 0 is the low one and 4 is the upper one, right? And if you know this is exponential function, right? So you have to go back to the first page or to the last section to look for this function right here, or this formula right here. and that will help you to integrate it out. Okay? Okay, moving on to the marginal analysis. What do we have here? We have already studied the marginal analysis in the context of derivatives and differentials in section 2.3 and 3.8. There, we were given a cost, a revenue, or a profit function, and we used the derivative to approximate the additional cost, revenue, or profit obtained by selling one additional unit, if you guys still remember, right? And then in this section, we will examine the reverse process. Okay, so just like what we learned from the past, derivatives and integrals, they are reverse of each other, right? They're like the opposite of each other. So for instance, suppose we wanted to find additional revenue obtained by increasing sales from X1 to X2 unit, say from like 40 units to 50 units, I don't know, something like that. Then we can definitely go ahead and apply the integration, and as you can guess, the 40 would be the lower limit, and the upper limit would be 50 in that case, right? If we knew the revenue function R, we could simply subtract R of X1 from R of X2. If we didn't know the revenue function, but we did know the marginal revenue function, we could still find the additional revenue by using the definite integral of X1 unit going to X2 unit, and then plug in the marginal revenue function in there, and then take the integral of it, and then just plug in the X1, X2 value, right? So, what does it mean? It's just exactly like the same thing that we learned in that first objective, but it involves more in terms of business. So they're still going to give you a function. They're going to give you some limits from where to where for us to go to. But then we have to do the setup. We have to set up our integral, and then we have to do the work and then get the final answer. Okay? So in short, for my question, we have the function in here. And as you can see, drdx is a marginal revenue, right? So, okay, just to clarify it out in here, drdx, this is marginal revenue. And if you just have revenue, it means revenue. Okay? So make sure you can tell the difference between the two symbols, between drdx and r. Okay, make sure you don't like mix them up, okay? So then, again, we have a function from the problem, and then we have the limits going from 500 all the way to 505, right? So to set it up, we're gonna have integration. 500 would be the lower one, 505 would be the upper one, and then copy and paste the function down right here. 900 divided by x, and then dx as for a compromise for the integral, right? Okay, so what we're gonna do from this one, there are two ways to do this one, or there could be like a lot of ways to do this one, but personally I'm gonna do the thing that the way that I think is like the shortest way, which is the way where I'm gonna go ahead and pull out a constant to the front, because we do have that as like one of the rule, right? Like 75 is a constant, so we can go ahead and pull it out, so then we don't have to worry about the integral of 75 anymore. Okay, so this is like one way to go for. I mean, like a lot of people, they may ask me like, can I just distribute the 75 into each of the two terms in the parentheses, because according to PEMDAS, we have to do parentheses first, right? And I'm going to tell you that's okay, but then imagine if you're going to multiply them, well, you're going to have to deal with bigger numbers, right? And personally, I don't like big numbers. That's why I'm going to go ahead and pull out the 75, okay? But if you want to distribute the 75 at the beginning, you can still do that, okay? So that's an option right there. And then let me stick with the red way, or the like pulling out 75 way, okay? So then on the inside, I'm going to get like 20 plus 900 divided by x still, right? Like nothing changes so far. And now, let's talk about the integral. Okay, first of all, let me just fix the x in here because it looks weird. Okay, next step, integral. So how do I do that? The 75, I'm just going to copy it down. The integral of 20 is 20x. The integral of 900x, it is 900 times ln of absolute value of x. Okay, and then what do I do? Well, I'm going to close them, and then the limit of integration, I have it going from 500 to 505. Wait, 5. Okay, so hopefully you guys remember how to do it now. For the upper limit, we're gonna grab 5 and plug it into wherever we have x in here and in here. Okay, and we're gonna go ahead and do the same thing for the 500 for the second row. Okay, so then the first number for the upper limit of 505, I got something like, calculator, 10,100. Okay, and then for the 500 row, I got 10,000 by itself. Okay, let me put a comma in there because there's so many zeros. Okay, and they're still within the parentheses, right? And then we still have the 75 on the outside, and in between, make sure you remember that's they are like in the difference relationship, meaning they subtract each other. There's a minus in here. Okay, make sure you don't get like confused. Okay, this minus coming from the fundamental theorem of calculus. Okay, so that's not a plus, that's not times, that's not division, it's a minus. Make sure you remember that. Okay, and if you put all that into the calculator for the final answer, you're gonna get 100. And this is all we do. Wait, 7,500, my bad. Okay, so 7,500. That's an ugly box, but there we go. Okay, so that's pretty much what you do for this one. So then the change in profit when sales increase from 500 to 505 units, it would be 7,500 products, or like dollars. Okay, so this one is $1 because this one is like, we're talking about the revenue, right? Revenue. So what does it mean? It means that like if you make 5 more products, if you make 5 more units, then you're gonna earn yourself $7,500, which is a good deal, right? So maybe they're talking about like iPads or something fancy like technology. That's why the price is so high like this. Okay. As for your part, you have this problem in here, and similarly, you have a function, you have a limit of integration, and if you need me, and if you want my help for the setup, it goes like integral of 200 to 300, and then copy and paste the function down here. I don't think I have enough space, so let me just move this thing over here. Okay, this is like good enough, I think. And let me circle the limits again, and then the function in here, let's put them in parentheses because they are together as a group. And just a heads up in here, there's like 3 zeros after the point. Okay, so make sure you don't like lose any of the zero. And then dx at the end to compromise for the integral. Okay, and after that you integrate your word, your function, plug in 300 and plug in 200, minus them off. There goes the answer. Okay, so now let's talk about the next objective, average value. Okay, it's pretty much the same thing as we did, but then for the average, what we're going to do is that we take the upper limit, we minus it with the lower limit, and we divide it. Okay, so then we're going to flip it over. So then the only thing that about the average in here is this one in here, where B is the upper limit and A in here would be the lower limit. Okay. So then pretty much this one we learned it from before already, and then we just have like this thing coming extra. Okay. So if x is a continuous function on a closed interval from a to b, then the average value of f on that interval from a to b is equal to 1 divided by b minus a times the integral. Okay. So then for the question for my part, I have to find the average value of this function right here, right? So then I have a function and I have the interval, so my a would be 0 and my b would be 1, or my lower limit is 0 and then my upper limit is 1, right? And after that, I also have to find all the x value in the interval for which your function is equal to its average value. Okay, so there's 2 parts of the problems, right? Okay, so let's break it down. First part first, the average. So what I'm going to do is that I'm going to do 1 divided by b minus a. My b in here is 1, my a in here is 0. And then times it by the integral going from a to b, which is 0 to 1. And I'm going to go ahead and copy down the function given from the problem, which is 4x divided by x squared plus 1 dx. Okay? This in here is 1, right? So I can just throw that away because we all know that 1 times whatever will return that whatever number, right? So for the inside out, this is like an interesting problem, right? So if you're stuck, if you have like no way to go, if you don't know what to do, think about use substitution. This is like something we learned from the past section. I don't remember what section it is, but like for one of the section, we talk about use substitution and it's really useful, right? So in here, what should we call for u, right? If you notice, we're gonna go for the higher power or a more complicated version or a more complicated problem, which is x squared plus 1 in here. Okay, it looks uglier, right? And then after that, you're gonna have to solve for x. But then unfortunately, in here, if you solve for x, you're gonna get like plus and minus something like square root, and that's ugly, right? So let's skip that. Because we might not need x even, right? So we don't even have to do x for now. But rather than that, we're gonna have to take the derivative of both sides. So in here, the derivative of x squared would be 2x, right? And then we're gonna put dx in here to even out with the differential u on the left-hand side, okay? And after that, what do? Well, we're gonna substitute back to the function that we have in here. So let me write it in here, I guess. Okay, so let me leave it as pink integral in there, and for 4x, I'm just gonna keep it as 4x. For x squared plus 1, I'm gonna get u, right? Oh, by the way, I forgot to solve for dx in here, so let me go back to orange and solve for my dx. It equals to du divided by 2x, right? And you will see why we need to solve for dx, because we do need some substitution for dx, right? And here's is the perfect time for it. So we're gonna go ahead and write out it as du divided by 2x, okay? So the 4x in here cancels out with a 2x in here, leaving us with a 2 in here, right? And then some of you guys may ask me, well, how about the 1 and 0, right? Okay, here comes the limit of integration. Let me put them in a box so it's easier for us to catch up with it. So we have two variables, right? The beginning one that we have is x, is coming from the problem. And then later on, we make up another like variable, we call it u. So those are the two variables that we have. For x, we have it going from 0 to 1. Okay, so what we're gonna have for u, right? So just imagine if we plug 0 into this x in here, we're gonna get 0 plus 1, which is 1, right? And if we plug 1 into this x in here, what do we get for u? We're gonna get 1 squared plus 1, which is 2, right? So then let me go ahead and just make these two in like different color, just so you guys know that these two are like the two values we get from plugging it back into the u substitution step, okay? And those are the new limit of integration that we have in here and here, okay? So at the end, what do we have? So we have it equal to, okay, I'm gonna go ahead and pull out a 2 because it's a constant, okay? And then we're still gonna have like 1 to 2 and then 1 divided by u du, right? And we all know that the integral of 1 over u is ln of u, right? So it goes like 2 ln of absolute value of u going from 1 to 2, okay? Okay, so let me like highlight this thing out because a lot of people, they miss it, and I don't want you guys to miss it. So let me put it in green. So limit of integration is going from 1 to 2. Okay, so if you notice, this bar in here is for integration. And this bar in here is for the absolute value. Okay, so you're going to have two bars. Okay, make sure you don't just end up having just one bar because it's going to look weird. Okay, and now as to continue on for the procedure, we all know that we have to go for the upper limit first. We plug it in, and then we're going to plug in the lower limit, right? So we're going to get something like 2 ln of 2 minus 2 ln of 1. Okay? 2 ln of 2 is a bad number, so even if you put it into the calculator, you're going to get like a decimal, right? But then ln of 1 is a nice number. If you plug it into the calculator, it should get you 0, I think, for ln of 1. Yeah, so this one has disappeared. So then the average value for this problem is going to be just 2 ln 2. Okay, so then this is what we do. Let me just make sure that the integral of 1 over u equals to ln of x. Yeah. Okay, and if you need more help on, like finding those information, I would suggest looking at the first page to look for this formula right here, where we have the integral of 1 over u, it equals to ln of absolute value of u. Okay. So, a lot of pages. Okay, so that's the answer. And then as for your part, you're gonna do this problem right here. Okay, so again, you have a function, and here's your limit of integration. Let me erase these. So you will have it going from 0 to 24, okay? And then this function and dt at the end, because we're using the variable t, not x anymore, okay? So make sure you don't get confused between x and t, okay? And what do we have in here? Okay, so find all x values in the integral for which the function is equal to its average value. So this is the average value. We have it already. That's good. And now we have to find the x value in the interval from 0 to 1. Okay, this is going to be ugly. Okay, so let's move on to the second part of the question. Let me put it in, I don't know, brow. Okay, so what we're going to do is that we're going to set the original function, which is 4x divided by x squared plus 1 equals to the average value, which is 2 ln 2. Okay, and then we're going to solve for x from there. And I don't know what you guys thinking. This is like ugly, right? So then first of all, 2 ln of 2, we can rewrite as 2 ln of 2 divided by 1. And after that, we're going to divide, we're going to do cross multiplication, right? So we're going to get something like 4x equals to, okay, in short, I'm going to distribute the 2 ln of 2 into the x squared and also into the 1. Okay, so I'm going to get something like, here, okay, x, you know what, let me just put the number thing first. 2 ln of 2 x squared and then plus 2 ln of 2. Let me go ahead and move this thing a little bit to the left so that I have more space to write in the 2 ln of 2. Okay, so now if you're not comfortable using 2 ln of 2 like me right now, you can definitely go for a decimal version of it, right? So then plug in 2 ln of 2 into the calculator, and you're gonna have it approximately equals to 1.39, right? So this is 1.39 and this is also 1.39, okay? And next up, we're gonna have to factor that, but before we do that, let's gather everything on one side of the problem. What do I mean by that? I mean, we're gonna minus the 4x on the left hand side, and we're gonna end up having something like orange. 1.39x squared minus 4x plus 1.39 equal to 0, okay? And I know this is like decimal, which is like bad, and I don't want you guys to do it out, but if you guys want, you can definitely use the, the quadratic formula, like the negative b plus minus the square root of b squared minus 4ac, all divided by 2a, right? And then from there, you're gonna get the answer. Or if you want, you can also look up the graph of them on decimals or GeoGebra, and it will also tells you the answer for the x's in here, okay? Or if you have like a Casio like me right now, you can just plug in like the function and it will tell you the number or the answers. Okay, so I have two x's. The first x, it equals to 2.47. The second x, I guess. Okay, it really doesn't matter for me if you call it like x1, x2, it's just, you know, like first x, second x. I don't pay attention to that much of detail, so don't worry too much about that. Okay, so these are the final answer that we get. Okay, and then did I put a star in your part? Yes, I did. Okay, so that's good. And now a little bit more on reviewing. So we have even odd functions from, you know, the algebra time. Okay, several common functions have graphs that are symmetric with respect to the y-axis, which means that f of negative x equals to f of x, showing that f of x is an even function. Or some of them might have the graphs that are symmetric with respect to the origin, which means that f of negative x equals to negative f of x. And that shows us that f of x in here is an odd function. Okay, so what's the highlight in here? Let me put red in here. Y-axis, it stands for even. Okay, even function. And the function for it would look like this. Like the negative will be canceled out if you notice. So this one in here is a perfect example for the even function. And why do I say it's a perfect example for the even function? Notice that this one is a y-axis, right? Okay, that's not a perfect like trace. Okay, that's all I get. Okay, so this is like the y function, right? And if you notice, the curve, the left curve in here is symmetric to the right curve in here, right? So this one in here is pretty much just like a mirror. And the left curve and the right curve, they are symmetric over with each other, right? They look the same. They like reflect over the y-axis, right? So this one is a perfect example for the even function. Okay, and the next scenario, odd function. We're gonna have the graph symmetric to over the origin, and here's a function for it. I'm not gonna tell you guys about a function, so you don't even have to worry if you don't understand these in here. But yeah, just keep in mind that y-axis is meant for even and origin it means for odd. Okay, so then this one in here is a perfect example for the odd function. And if you want me to point out, here we go. Here's the origin, right? And if you notice, this curve in here, the right piece is symmetric with the left piece over the origin, right? So this in here is a mirror now. Okay, and then this is the odd function. Okay. Okay, so why do we have to do that? Why do we have to learn about it, right? We're gonna talk about this one. Okay, but before that, let's talk about the graphs in here. So just like what we had shown in the two graphs, in the red circle and also in the pink circle in here, this one in here is an example for odd, where it's symmetric over the origin, and this one in here is a perfect example for the even function, where we have it symmetric over the y-axis, right? And if you want me to do the same steps over again, y-axis is this one, and then this piece, it is symmetric over this piece. Okay, and if you look at the coordinate for this one, the y coordinates are the same, but only the axis change, right? That's what it means in here. The axis, they change, but then the y part, they equal. Okay. As for the pink in here, or for the even function, or no, odd function in here, we will have origin as a mirror, and then this piece, I can do a better job. Okay, it's harder. Okay, this piece in here is symmetric to this piece in here, right? And if you notice, not only the x change, but the y also change, right? So the x changes, and the y, it also changes. Okay, and what do I mean by the y? I mean the f in here. If you notice, for the red one in here, f equals to f, right? But for the pink one in here, f equals to negative f, just like how y equals to negative y. Okay? then more information, even function in here, odd function in here. Okay, so why do we learn it? How can we connect it to the integrals, right? For even function, because they're symmetric over the y-axis, so instead of finding like the area underneath, you know what? Okay, here, let me give you a specific example rather than just talk about it in general. Okay, so this one is, was it even, right? So even, let's do red. Let's see if I'm gonna ask you guys to find the area underneath of the curve in here for the shaded region. This one in here. Okay, what are you gonna do? You guys gonna set it up as the integral of the function, which is x squared dx, going from where? Going from -2 to 2, right? So it's -2 to 2, right? So we all know that we're gonna have it integrated like x cubed divided by 3 and then plugged in, blah, blah, blah. We're gonna get the answer, right? So a number in here, I'm not gonna do it out. You know what? Actually, I think I can do it out. So 2 cubed divided by 3. Okay, so all the work after like the subtraction, you're gonna get something like 16 divided by 3. If you want to check that work with me. Okay? In another scenario, like we're gonna have this problem, but because x squared is the even function, right? So instead of having it from -2 to 2, I only need to find the area of this piece in here, of this positive area right here from 0 to 2, and I'm gonna double it up because the left circle equals to the right circle in areas, right? So I don't have to do a lot. Okay, here's the second way, and let me put it in, I don't know, blue. The second way, instead of doing this, I'm gonna do it from 0 to 2, like halfway, right, of the same function, and I'm gonna double it up. Okay, so this one in here, the 2 is outside, so I'm gonna keep it outside, and then times it by x cubed divided by 3, going from 0 to 2. If you do it correctly and then you times 2, you're gonna end up having the same number, same answer as 16 divided by 3. Okay, and these are the same. Okay, so as for the formula in here, to break it down for even function, we can just break it down at 0 and then we double it up by 2. Okay, so then you don't have to deal with the negative numbers, because sometimes, you know, you might trip and then negative numbers might kill you. Okay, all right, so that's for the even case. How about the odd case, right? So let me go ahead and cut this thing off. Okay, odd function, let me put it in pink, color code. Okay, so say if I'm gonna give you this picture right here, and I'm gonna ask you for the area of the shaded region, which is like underneath of the curve and above the curve, right? So to set it up, what do we do? Well, we're gonna have it going from -1 to 1, just like how we usually do it, right? And the function in here is x cubed dx, right? In a regular way, we all know how to integrate this, so it goes like x4 divided by 4, going from -1 to 1. And if you do it correctly, after you got like the upper limit, the lower limit plugged in, and then you subtract them, you're gonna get a 0, right? However, there's another way to do it, right? If you notice this power in here, I mean this area in here, area, it's a positive area, right? Why is it so? Because it's above the x-axis. Okay, and the area in here, it's a negative area. Why is that so? Because it's below the area. Okay, so let me highlight it down. This one, I don't know, green, above, so it's like plus, and the other one below, so it's negative. Okay, so in short, they cancel each other out, right? Because the blue one in here, it looks exactly the same area as the green one in here, but it's just like, you know, upside down, like roller coaster, right? So then if you add them together, you're gonna get a 0, just like what we expect in here, right? So then, as a quick trick, area of an odd function going from a negative value to that positive value, say from -1 to 1 or -2 to 2 or even -3 to 3 or even -10,000 to 10,000, you're always going to end up having 0. So in general, if you have it going from -a to a, and f of x in here is an odd function, the answer is always going to be 0. Okay? All right, just to point out really quick before we move on is that this area, sometimes some people might ask me, like, why don't we have the same scenario in here? Because we do have like two areas, one on the left and one on the right, right? And I'm going to tell you this area on the left hand side here is still a positive area. Why is that so? Because it's above. Okay, that's an ugly above. Okay, this one is above the x-axis, right? Above, yeah. It's on the left-hand side of y-axis, but it's still above the x-axis, right? Which means it's still positive. And then for the other one, it's going to be also positive because it's still above the x-axis, right? So when it comes to positive or negative area, you always have to compare it with the x-axis, not the y-axis. Okay? So let me highlight this one now. Okay? And now, finally, the last objective of the day, annuity. Okay, so it's pretty much just like I give you the formula, you plug it into the formula, you get the answer. Okay, so this one is like pretty much straightforward. In terms of business, I'm not sure how many of you guys will go into like financing or, you know, like this annuity. So I will just like cover it just in case you guys might see it in the future. Okay, so a sequence of equal payments made at regular time intervals over a period of time is called an annuity. Some examples of annuities are payrolls, saving plans, monthly home mortgage payments, and individual retirement accounts. So those are like the example of annuity, right? And then how can we compute the amount of an annuity? Let C represent a continuous income function in dollars per year. What T is the time in years. R in here represent the interest rate compounded continuously, and T represents the term of the annuity in years. Then the amount of an annuity is calculated by this formula in here. It's going to be long, so I'm not going to read it out. But we do have a formula in here, right? So you know what to do. Next up, we just like plug in the formula and then get the answer, right? So for my part, let's just do it out. This one obviously is going to be a rate, right? But then we all know that we cannot use 8%. So we have to convert it back into decimal, which is 0.08. Okay. 6 years in here. This one obviously is the time. So this is the big T. Okay. Okay, let me just write down. Big T equals 6. So we get R, we get T, that's really good. And the last thing that we have to get is the CT. And CT in here, or C in here, would be the amount, like, the amount of money that you deposit in your account, like, originally, okay? So, as you can guess, this one is our CT. Okay, so we have everything ready. Let's plug in the formula right here to find the annuity, okay? So it goes like e to the RT, which means we're going to get 0.08 times 6. And then after that, we're going to have the integral going from 0 to 6. And then CT for 250 times e to the negative RT dt. Okay, so just a heads up in here, we have two type T's, right? Like the big T and the small t. The big T in here is a number always, and the T in here is a variable. So you make sure you don't touch on the small t, okay? So the small t from the formula, it just stays as small t, okay? Big T has to be a number, but small t, it stays as a variable. As you guys can see in here, there's a T in here and there's a T in here. We don't touch on the small t's, okay? And then we pretty much will do like the integral for here. Okay, so let me pull out the 250 to the front. Why? Because 250 is a constant, right? And at the same time, I'm going to go ahead and multiply the 6 with the 0.08 too. Okay? So in short, it equals to 250 e to the 0.48, going from 0 to 6. And then the function is still the same. It's e to the negative 0.08 t dt, right? And then after that, here comes the integral part. So I'm going to go ahead and rewrite the constant part because we're not going to integrate anything with the number or whatever number you have in front of the integral, right? But after that though, for this part, what is the integral of e to the something, right? It is itself e to the negative 0.08 t, but then divided by whatever number you have in front of the variable, which is negative 0.08. Okay, and then the limit of integration, it goes from 0 to 6. So let's plug it in there. So then again, I'm going to go ahead and copy and paste this number down. So 250 e to the 0.48, and then if you were to do the math correctly in here, after you plug in 6, and after you plug in 0, and after you subtract them, you're going to get something like, give me 1 second. So e to the negative 0.8 times 6 divided by this. Okay, so for the first one, I got negative 7.73. And as for the second one, I'm going to get, what is it? Negative 12.5. Okay, and make sure you have like 2 negatives. This is coming from the fundamental theorem of calculus formula. Okay, and if you want the exact form, you can also do that, right? Like if you want the exact form in case, you can always do it like 250 e to the 0.48, and then for the other one, you have something like e to the negative. Okay, after you times 6, you're gonna get like 0.48, right? And then the bottom would be 0. That, and then minus e to the 0 would be just 1. Okay. This is like just in case you want like the exact form. Okay. And after that, you can go ahead and pull out the negative 0.08 out to the front, and then if you want the exact form, it's gonna look like negative 3125 plus 3125 e to the 0.48. And this is because I go ahead and I distribute the 250 e to the 0.48 into each of the term of the parentheses. Okay, and if you know this power, it cancels with the negative version of it, right? And this in here, if you multiply with the 1, you end up having this. Okay? And if you don't like it in the exact form, it'll question it asking you to route the answer to, I don't know, like certain decimal places, like 2 decimal places. Then you can put it into the calculator, which will give you something like 1925.23. So this is the annuity that you get after you deposit $250 within 6 years. Okay, so this is the final answer. Okay, so for annuity, it's pretty much just straightforward. Like you plug in the formula. Make sure you remember formula though, or like have it written down on the paper, a piece of paper, so you have in front of you when you do homework or assessment. But anyways, this is what you have to do for your part, and I think that should be the end of this section. So thank you for your listening. If you have any questions, let me know. Email me, text me, and group me. Just contact me, okay? Thank you for your listening. Take care and have a great day. Bye-bye.